All right, so we're finally there to chapter 6. Right? Why is chapter 6 kind of our arrival point? Well, because it's potential sweep. So we're finally going to be able to scan here. As I said, this is where we'll spend the majority of our time, but then we're going to go skipping through the technical calculus. All right, so again, we almost kind of gave it away because we just spent a whole bunch of time with sample voltammetry, and I told you, well, sample voltammetry, sweeping is just like doing all that sampling, except you don't have to keep going back down to that. So if you think about it, right, if we're going to sweep, oops, I'm not going to draw my favorite graph first. We're going to do some sort of sweep, right? And we can start out at some initial time, at initial potential, and then we'll sweep upwards, right? And so we'll get that our potential is equal to whatever our initial potential is times v. Little v is scan rate. We'll keep seeing a lot of times time. So right, we can look at that, and then right, we can kind of plot the voltage that we get with potential. And so, right, we've already made this plot like many times today. And so we get this plot, right, of current versus voltage. But notice that you really have 3 dimensions of data. All right, and those 3 dimensions of data are I, E, and time. All right, so in our lab, we solved the problem of the fact that we have 3 dimensions. Well, we don't really. We have a different time, right? But so potential, the potential varies with time, current versus. So you could do this graph as a function of time. In fact, when you output CVs off the old Target program, at least when you output the CVs, annoyingly to some people, it gives you both the time and the potential. So you could plot it either way. Now, most of the time we just chuck the time and plot it versus potential, right? But either or, they're the same thing, right? And so I drew you a nice one right here, right where I said we were stirring, but we didn't really consider last time the case too much of what happens if we don't stir. So let's talk about if we don't stir. If we don't stir, our potential is going to look, our current versus potential curve is going to look something like this. And it's going to start to come down after a peak. Why does it start to come down? Diffusion. So what does that mean?
There's not enough reactants on the surface.
Right, there's not enough reactants near the surface. Again, we're not going to talk absorption for the moment. All the stuff that was near the electrode got used up. When I'm going up here, right, all of this is things getting oxidized or reduced, depending on what convention we're using, right? And then it reaches some sort of peak between the potential is high enough to drive the reaction, and there's enough stuff there, and then it starts to fall back down. So it starts to fall off, right, because we've depleted our analyte, again, at the electrode surface. Because think about it, is more voltage better for doing the reaction? I mean, to a certain point, yes, until you're so far, beyond there. But so it's not that you can't do the reaction. You have plenty of energy to be able to do the reaction. It's just that you don't have a molecule staying around there. And so if we look at the concentration profiles. This is the concentration, again, this is my electrode surface, this is distance from my electrode, where 0 is going to be the electrode surface. We're going to look at the booklets as an example for an actual molecule, they call it anthracene. So A plus electrode makes a radical negative charged anthracene, right? And so we would have some sort of bulk concentration of A. Right, and over time, that would drop off. And then we make a product, right? So the product has the opposite sort of opposite sort of curve, right? Where because we're making it right there, it's got its largest concentration there, it spreads out as we go away. Okay, so that's linear sweep. We love that. What if we go back down? You like that even more. Right, so now we go up, right, and then we'll come back down. Something like that. And if we do that, we'll get a cyclic voltammetrogram. Oh, this is awful. It's not my best. I once got points off my electrochemistry grade exam in graduate school because Doris Murray said my cyclic voltammetrograms were ugly. And they didn't look right. So I said, I haven't gotten any better at drawing. We would get something like this. So here's always the tricky thing to remember. Your electrode doesn't know what direction you're scanning. Right, so as you go up, let's say this is our lab, like this is a slope scan of dopamine. We'll use our convention. So let's say this is oxidation of dopamine. What reaction are you doing right here? As we go up, we oxidize dopamine. Where I made the mark. What's happening right there? You have two choices. It's either oxidation of dopamine or it's reduction of dopamine.
So oxidation.
All right, let's take a vote. How many people vote for oxidation? Okay, how many people vote for reduction? All right, the oxidation people win. Right, your electrode doesn't know that you switched directions. Right, it doesn't know that. It doesn't know what what you're going to do. So all it cares is whether or not it's at an energy sufficient to do the reaction. So if there's stuff there, it's going to continue to oxidize even though you went back the other way. Now, of course, we actually see this in the lab all the time when we see our stupid adenosine oxidation peaks and histamine and all those other things that we do are not very ideal on the backside of the reaction, right? So I think you know that, I think, if I pull up those molecules and those ugly CVs, you kind of know that from experience, that just because you went the other way doesn't mean you automatically do a reduction, right? If you're at a potential that's sufficient to do the reaction, you might still be doing the reaction. So yeah, this is always the trick question, right? We're still doing oxidation even there. Right, we have to get doing a potential sufficient to do a reduction to start to get a reductive current. And it turns out, I didn't do this very well. You really if you want to measure the oxidative current, not so bad, so we can measure the peak oxidative current. If you wanted to measure the peak reductive current, you can't just measure it from 0, because that wasn't your baseline. As this comes down, it makes a funny sort of thing, and if you extend the line off of it, you can measure a cathodic current. And if this was reversible, I didn't draw it very well, because, right, IPC should be equal to IPA. But not from 0. Again, the IPC will always not go as far down as possible. If anyone ever works with our PINE system, which we use for the undergraduate teaching lab, I think a few people over is using it for some research, it will actually automatically calculate these things. You can just, click 2 points, tell it to put the line there, and it'll calculate the IPCs and stuff for you. So regular electrochemistry software is sort of used to doing that, right? So you got to get this to a potential sufficient to look at that. And so we'll kind of do that. Okay, so it turns out that you can write a lot of equations, which I'm going to skip. I'm just going to skip to the answer to figure out what's that peak current. You can read the book if you want to look and see how this is derived. Okay, so it turns out you can write an equation for the peak current at at this cyclic voltammeter. It has some funky constant, if you remember about that. End of the 3 halves. Gotta love that. You guys know see that kind of a thing. A, D, 0 to the 1/2, so diffusion constant. But the things you would expect, right? Diffusion, concentration, scan rate, area, number of electrons, right? All those variables we keep seeing in most of the equations are in this equation. And so this is the equation. So yesterday we did the Ch equation. I told you, we were looking at, and it had a t to the 1/2 in the bottom. Had a t to the minus 1/2, and I said that's where it comes from. Again, you have to go through that to get here. But this is the equation, right, that tells you that I, peak, right, should be proportional to v to the 1/2. So what is this assuming? Of course, right, like everything else, this is always assuming that we have a diffusion controlled reaction. So this is the textbook electrochemistry that says I is proportional to v to the 1/2. And I really mean in my undergrad, so I make them solve this equation for something. Area electric, I can't remember, no?
Yeah, it's something diffusion constant.
Diffusion coefficient, that's to solve it for. So there's a trick, though, and I'm not being mean to my electrodes, but that I'm not mean to my undergrads, I tell them this. I forgot to tell you up until this point. If you wanted to go solve any of these equations, again, like any equation, you should sit down and figure out the units of everything and make sure that they can cancel. And if you were to do that, you would figure out that the units of concentration are not molar. So concentration in all of these equations I've been showing you so far is not molarity, right? It's because moles per liter. Anyone know what a liter is? Turns out to be a decimeter cubed. And so in this case, the units for concentration, the correct units for concentration are moles per centimeter cubed, because all of the diffusion coefficients are done in centimeters. All of the areas are done in centimeters. So then you do your concentration in centimeters. And as long as you're on board with this, and you convert your molar to moles per centimeter cubed, you're all fine. But if you start throwing your molarities in there, you will screw up your answer. In fact, I think Chris Jacobs and I were solving some of these equations once. And when it dawned on me that I knew this, that we had the concentrations wrong, and that's why our orders of magnitude are, because, the difference between this is 10 cubed, right? So that's a 1,000-fold difference. So your radius of your electrode ain't anywhere close, if you get the concentration wrong in these equations. They're all like this, all in centimeters, moles per centimeter cubed. So that steady-state disk equation that I was showing you, we're solving it with the wrong concentration. I was like, light bulb, I know that. I know that I'm using the wrong concentration. So use the right concentration. Don't be silly. But when you are silly, then you'll be like, oh yeah, I remember. Somebody told me that once. That I shouldn't get that. So let's look at. All right. So there's equations then. There's my right here. For E peak. So E peak ends up being E to the 1/2 minus 1.109. This is not an equation I really want you to memorize, but I want to look at it. Over NF. This whole thing ends up being about 28.5 millivolts over N, which just happens to be half of 59, right? So you're kind of like halfway. So if I was to write E to the 1/2 on here, right? All right, we're there, and then we're kind of up to E peak. And there's a slightly different one where people will do EP to 1/2. But let's look at this thing. So this is what theory tells you. E peak is equal to E to the 1/2 minus 1.109 times RT over NF. So how does that vary with scan rate? Okay, let's go for the obvious question. Is scan rate an equation? No. Is voltage in the equation really? This is the thermodynamics of energy, right? There's nothing to do with what I applied to my electrode, right, in the equation. So scan rate's not in the equation. And so this theory then tells you that EP is independent of scan rate. So the textbook tells you that your potential should not change with scan rate. When we talk FSD, we'll come back to that. But that's what the textbook tells you, because you've done the experiment. Does your potential change with scan rate? Who's done this experiment recently? Shannon, have you done scan rate recently?
Yeah.
Yeah. Does your potential change? Does your potential shift?
Yeah.
Yes, right? Yes. So you're breaking the textbook. You just didn't know it. And so that's why I have to teach you the textbook, so you can figure out all the rules you just broke. So we'll have to think about, why is it that our potential shifts? Because it shouldn't. Textbook says it shouldn't change. It shouldn't matter how fast you go. It should always be in the same place. But if you do this experiment, usually if you plot the CDs on top of each other, you'll see them nicely move out with scan rate. So again, we're breaking the textbook here. We'll get back to that at the end. And again, you can use this to kind of look at that. Turns out, though, that there's a funny thing happens when you get to a microelectrode. So we're used to seeing, everybody loves to show you these CDs that look like this. Turns out that if you have a microelectrode where your scan rate is much less than this here, RT over NF times D over R squared, right, this is our electrode. Then instead of getting that duck-shaped kind of curve, what you end up getting is a steady state curve. So we're back to where it looks like that limiting curve that I showed you. So I don't know, has anybody gone really slow in this lab? I mean, we have, Hillary, have you done like 1 volt per second? Did you see something that looked more like this? Yeah. So we have small electrodes, and so we don't even get this. As I said, this is the theory. You actually end up getting a steady state voltammogram if you do it. Sometimes when we do it in the lab, we just see the tiniest little peaks. But depending on if your electrode is small enough compared to the diffusion coefficient. Sorry, scan rate is small compared to the diffusion coefficient and the radius. You actually it turns out that you're going to be able to sample and get a steady state current. So that's sort of interesting. Okay, so let's go to a cyclic voltammogram then. I have one drawn. Let's reiterate the obvious. So the things that are of interest when we look at cyclic voltammogram are oftentimes IPA, particularly how it relates to IPC, right? Because if that was to equal 1, then we would be really happy because that would be reversible. The other thing that we want to look at ends up being delta E peak, and so we can come up with a, maybe better. Again, I'm drawing these like our current conventions, so this would be like oxidation of dopamine, right? Where we look at delta E peak is EPA minus EPC, so not current minus cathodic current. So we look at that difference. It turns out that difference, again, ends up being this 2.303 RT over NF number, right, which we already learned is 59 millivolts. This is why we need to know it, because it should be 59 millivolts over N. So for dopamine, then, what should be the peak split? 29.5, yeah, I would take 30, so you can do the math. Right, like 60 divided by 2, right, because N is equal to 2 for dopamine, again, hopefully you know that. Dopamine is a 2-electron process. So for dopamine, right, our expected peak splitting is 30 millivolts. Wow, right? I mean, again, this is where you have to know that your cyclic voltammogram just looks so strange, right? I mean, because what's a typical delta E peak in all that?
0.8 volts.
Yeah, like 800 millivolts, somewhere between 600 and 800 millivolts. I always usually get numbers in about the 700 range. I mean, traditionally people have said the oxidation peak comes at 0.6, the reduction peak comes at minus 0.2, so that would give you the 800 that Scott said. I just find that mine are usually a little closer together than that, like 700 millimoles, something like that. But right, 700 millimoles, 800 millimoles, right? I mean, nobody needs 30 millimoles, right? I mean, it's not even close. It's not even like you're kind of close, you know, am I on the borderline? No, you're not even close. It's not even close to being ideal, right? It's so far away. Okay, and then I think we'll skip multi-component systems, only to say this. Right, so if you had two things, maybe not half bad. You could get voltammograms that kind of look like that, right? But the closer and closer their E1 halves or E formal potentials are, the more you'll get kind of, muddled messes where they merge together. And again, this is one of the disadvantages of electrochemistry. So electrochemistry is cheap, right? It tells you something about the charge state of the molecule, which is good. It's not the best at selectivity. Meaning the differences, and again, if I was a P chemist, I would say it this way, the differences in delta G that it can discriminate are not as good as other methods. So, you have to have a pretty substantial difference in energy to be able to really discriminate things. So processes that are about the same energy, we aren't really able to discriminate. And so, we get muddled messes as far as that goes. Okay. So let's skip ahead to chapter 11.